All right, the last part of review talks about percent yield. So our equation is actual divided by theoretical times 100%. So I say this is what actually was made in the lab divided by, in theory, what should be made times 100%. I equate it to saying, on a test, you should theoretically get 100, but what you actually score is an 80. So what your percentage is you got an 80% on that test. So I'm looking here. And it says the theoretical yield of a particular reaction is 5.67 grams. So theoretical, that's going to go on the bottom. Then what is actually produced in the actual equation, the reaction is 3.19 grams. This becomes a simple problem of taking the top number divided by the bottom number to give you your percentage, and you end up with 0.563. Again, you multiply that by 100, and you get 56.3%. Same thing here on question 2. Right through, I got to figure out which one is the actual, meaning what did they do in the lab, and which one is the theoretical, what should take place. So they produce 5.06 grams of barium nitrate, but the expected result, that's a way of saying that's what theoretically should have been made. 8.85 grams will be on the bottom, 5.06 grams will be on the top. I'm going to multiply that by 100%. It's going to give me 57.2% is my total. Now scroll down here to the last question. It's the same type of question, but we have to set up a Stoich calculation before we do our question. So let's balance our chemical equation real fast. I'm going to use a different colored pen here. Okay. So in a reaction of iron and oxygen to produce iron 3 oxide, 2.1 grams of iron were completely consumed. What is the percent yield if 2.5 grams of iron is actually produced? So if we're looking at this, we have the actual, we need to come up with the theoretical for our equation. So we start off with what they gave us, 2.1 grams. This is what actually took place in the lab. So we start off with 2.1 grams of iron. And so the first thing we got to do is we got to figure out what is the molar mass of iron. We go back to our periodic table. And we discover that iron is 55.845 for every 1 mole. All right, so now we have to cancel out the units of moles of iron. Well, in our equation we have 4 moles of iron. And this is we're going to do the mole, do the mole cross bridge. We're going to go from the moles of iron again into the moles of iron oxide. So we have 2 moles of iron oxide in our equation. So our units cancel there. And now for every 1 mole of iron oxide, we have to calculate that mass. So we have iron here and oxygen. So in our equation we have 3 oxygens, so we need to take this number times 3, and we have 2 irons, so we take this number right here, the mass of iron, we multiply that by 2, and we come up with a total of 159.66 grams. So now what we're going to do is we're going to calculate the total for our mass. So we take 2.1 times 2 times 159.66. So that's the number for the top. Then we're going to divide it by the number on the bottom, which is going to be 55.845 times 4. So I'm going to put that in parentheses. 55.845 times 4, close parentheses, gives me a total of 3.0. We're going to be keeping 2 significant digits here, so I'm going to keep 2 of those one of those decimal places. Now that's what theoretically should be produced in the lab. What was actually produced? 2.5. So we take 2.5 divided by 3, multiplied by 100 for a total of 88.3%.